Hey there, my name is Alejandro, and welcome back for day 232 of me doing Daily LeetCode challenge after I reach 1 year's worth of great contributions here on GitHub. So today's problem is for March 5th, 2025, and without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 2579, count total number of colored cells. Sorry, there exists an infinitely large two-dimensional grid of uncolored unit cells. You're given a positive integer n, indicating that you must do the following routine for n minutes. At the first minute, color any arbitrary unit cell blue. Every minute thereafter, color blue every uncolored cell that touches a blue cell, okay? Below is a pictorial representation of the state of the grid after minutes 1, 2, and 3. Okay. Return the number of colored cells at the end of n minutes. Oh, I see. Well, the easiest way would be to do this via simulation. But... okay, n is the number of steps, right? Yeah. Okay, so this should be like some mathematical formula pretty much. I'll just have to figure it out. So here we go, 1 to 4. Let's see if we can find a pattern, I guess. 2, 3. Sorry, by the way, I'm a little bit sick. It's a bit hard for me to speak, so I hope that's not too much of an issue. Okay, let's see if we can find a pattern here, right? This is like a good machine learning problem almost. Sorry. Case 1. Here we'll just do return -1. Is that the problem? Okay, so it expected 1, 5, 13, 25, 41. So let's write this down. 1, 5, 13, 45, 25, 41, right? 13, 25, 41. Interesting. Here we can add n is equal to 6. So yeah, so immediately it's not immediately obvious how the pattern's gonna go. 41 and 61 is interesting. I wonder if there's gonna be like 81 or something. I actually want to add a few more. Let's do 7. 8, and then we'll kind of stop there. So for 7, it should be 85. Interesting. For case 8, it should be 113. Is the next one like 125? Okay, I'm actually kind of curious. What if we add one more test case? Yeah, let's do 9. Okay. Oh, case 1 is now 9. Case 1 expected 145. Okay, so there's definitely some kind of pattern going on here. We'll have to figure out what that pattern is. Yeah, one way is obviously to simulate things, so we could definitely do something like that, right? Right, something like you have Q, n is at least equal to 1. If Q is equal to collections dot deck, here we'll just have 0, 0. Or here we'll just say origin is equal to 0, 0. We'll just have the origin in here. Visited is equal to a set with the origin in it. Here we'll do for this in range n minus 1. There's another level of exploration, right? But really, oh wait, this is simpler than that, right? From the original square, right? If n is equal to 3, that means I can do at most 3 blocks in any distance, right? At most 3. So it's like here, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It'll always keep this type of pattern, right? So it's like, yeah, 1, 1, 2, 3, 4, 5, 13, Yeah, so this will be a 1 by 1 with 4 sides. So it'll be a 3 by 3 with 4 sides. So 9 plus 4. 21. Yeah, what does the case 4 look like, right? This will be something like, it'll be hashtag, hashtag. So these, oh, we're just gonna add, okay, this is bizarre. Oh no. Pretty much we just add 4. We'll start building a square at some points, right? Right, so if this is the origin, then we can go, okay, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Let's say that this guy's the origin, right? You can go 4 this way, 4 this way, 4 this way. We'll call it O for origin. Or it can go 1, 2, 3, 4. So here we'll just do this, 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 this. These will be hashtags, 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 which should really only be 3 in each direction. All right, 1, 2, 3. And it can only go up that much. So each diagonal takes 2. So it can go at most 2 diagonal. Right, but nothing more. You can definitely reach that. You can definitely reach that. Now this guy. Now these are gonna be mirrored. I can definitely reach these, but not these, right? So it's like you can reach all the way up here. You can go 1, 2, 3, 4. 1, 2, 3, 4. What, 1? Okay. No, 1. So 1, 2, 3. I actually can't reach this guy, right? So yeah, this becomes a pyramid-like shape almost. Like this. Tack, 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 tack. Is this right? No. Oh, do I just have an extra here? How much is there? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 17. 17 plus 6 is 23. 24, 25, right? This is indeed, yeah. So whenever it forms this nice little, yeah, there's definitely a pattern to this thing. But now the thing is, okay, this is a 1, 2, 3. Yeah, it's not necessarily a box with 4 sides, right? Yeah, there's gonna be some type of math problem. Yeah, it would just be nice to obviously see the more examples, right? Because I don't think I can simulate this. Right, with n to 10 to the 5. I mean, I can allow myself to reach everything that's up to 10 to the 5 away in distance. Yeah, it's basically how many points are a certain maze distance away. Maybe I could calculate that. But it's like if I can go a distance of, yeah, if I can go a distance of 1, then there's nothing. If I can go, if a distance of 0, there's nothing. If we can go a distance of 1, I essentially have 4 options. Distance of 2, I have this option, this option, this option, this option, this option, this option, right? And essentially, the direction I have 4 options at the very beginning, and then from each of those I have 3 options. But I can't count already neighbored cells. Right, because one way I can do things is essentially, you know, q is greater than 0. I'll say x comma y is equal to q dot pop left. If x plus y greater than n, right? So like here, like 0, 0, or here it'll be 1, 0. Or 0, 1. Right. Say for, here we'll say directions is equal to 0, comma negative 1, 0, comma 1, negative 1, comma 0, 1, comma 0. Dx dy in directions, neighbor x, neighbor y is equal to x plus dx, y plus dy. If neighbor x, neighbor y visited, then continue. Otherwise, here we'll say dot add neighbor x, neighbor y, q dot append neighbor x, neighbor y. Right, and something like this, return length of as if it's set. Uh-oh. Memory limit exceeded. That's interesting. Print f string x comma y equals. I'm very interested to see. Oh, absolute value of x plus absolute value of y. That's definitely important. Dist is equal to absolute value of x plus absolute value of y. Dist is greater than or equal to this. Assert dist is equal to that. There we go. Okay, so yeah, so it's accepted for all these cases, obviously. But yeah, something like this might be too slow is what I'm guessing. Forgive me. Yeah, MLE makes sense. So we're gonna need some kind of mathematical formula for this. So yeah, is it just gonna be literally just try to find the pattern? I mean, I'm always adding this much, this much, this much, this much, so that it becomes more, right? I'm always adding 1, 2, 3, 2, 3, 1, 2, 3, right? From this guy, we'll say, oh, this was part of the 3. This was part of the 3. 3, 3, 3, 3, 3, 3. So we're these guys, right? 3, 3, 3. Okay. So what we added was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for 4, we added 4 times 3. For 3, we added 3 times 3, right? Did we add 9? 5 plus 9 is 14, not 13. Did I count this right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, Yeah, this is 12 more than 13. 1, 2, 3, 4, 5, 6, 7, 8. Oh yes, this is 8 more. Where will 8 come from? Yeah, so basically we're adding one more border like this. 8. So essentially we have that 4 maps to 12. 3 maps to 8. 2 maps to 4. 1 maps to 0. So, okay, would something like 5 map to 16 is the question. We've cracked the code, I think. Okay. Python 3, 25 plus 16. Yeah, then 41 plus 20. Yep, now this plus 20, 61 plus 24. Yep, is 85. 85 plus 29. Ooh, oh no, plus 28. Yeah, okay, there we go. Nice. Then this plus 113 plus 32. Yeah, okay. Okay. So it'll be colored cells of n times 4 equals 2 times 4 equals 3 times 4 is equal to 4 times n minus 1 plus colored cells of n minus 1. Return 1, otherwise 4 times n minus 1 plus self.colored cells of n minus 1. Does something like this work? It does indeed. Let's submit. And there we go. Completion streak 232 days. Consistency is key. See ya tomorrow. Yeah, that's exactly right. So this just happens to be a mathematical formula. Yeah, we can do this a little bit better, obviously. Okay, so what we want is essentially what this is going to look like is this is going to be 1 plus 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4. This is really 4 to the 0. 1, yeah. Okay. So it's sums of powers of 4. No. Not powers of 4, multiples of 4. 1 plus multiples of 4. Or just multiples of 4. Result is 1 plus. Let's do return 1 plus sum of 4 times. Oh, wait. We can take out the 4. Yeah, so what I'm saying is this. 4 times c for c in range 1 all the way up to n minus 1, but including that one. Right, so that works. Okay, we're at 112 in mass, but we can do one better, which is this will be this 4 times that. That will also work. Beautiful. And so here, here we'll just do sum of range of 1 comma n. Right? And now, better yet, the sum of the first n numbers is equal to, this will be from 1 to n minus 1. So it'll be n minus 1 times n minus 1 plus 1 all over 2, right? So this will be something like return 1 plus 4 times, this will be n minus 1 times n minus 1 plus 1, which is just n, all over 2. Yep, and we can submit this. And there we go. That's how we get 0ms. Bada bing, bada boom. Heck yeah! Okay, nice. Yeah. I'll put this in parentheses. Times n. There we go. Yeah, so this is obviously 0ms because now it's just like, you know, a little mathematical formula. So, okay, so as always, in all my videos, I do a quick recap of how I will solve the problem. So for this one, essentially, again, we want to count the total number of colored cells. So the point is that we start off with one box at n is equal to 1, and essentially we keep expanding as n gets larger, right? N equals 2 means you can go up to 1 distance away from the origin point, right? So 1, 1, 1, 1. N equals 3 means you can go up to a 3, right? So here's like, you know, 1, 2, 3, or you can go 1, 2, 3, or you can go 1, 2, 3, right? It's like you can only go up to a max distance of 3 or a max distance of 2 away from yourself, right? Basically, what are the number of cells that you can reach from the origin going n minus 1 steps away from the origin, right? Or the way that they describe the problem is like infinitely large grid of uncolored unit cells. You're given an integer n, and at first minute you can color any arbitrary unit cell blue. Every minute thereafter, color blue every uncolored cell that touches a blue cell, right? But you can think of this as just like, you know, an expansive BFS. And so I realized pretty quickly that since n is equal to 10 to the 5, this is probably going to be like, you know, some type of mathematical equation, right? The very first thing that I did is like, okay, let's solve this like as if though it was a regular graph problem, but obviously I already knew since n is 10 to the 5, this is just going to be way too slow, right? Yeah, I mean, we tried that, but that was that obviously that actually MLE did, even TLE. But the point of this problem is essentially you got to try to recognize the pattern, and so that's what I was trying to do over here and so on. And what I realized is that essentially we're always just adding a border, and the border is always proportional to the value of n. So here, for example, n is equal to 1. We can think of it as we just have 1 square, right? The center we can just think of as we always have. So you'll see in my solution we have 1 plus something, right? So we think of the center as something we already have. Now, the way to think about this problem is in terms of blocks we add. So here we added 4 blocks. We added this guy, this guy, and this guy, and this guy. Then to this guy, we added this chain. So if we think of this cross, right? And this cross is right here. Everything that is not this cross, right, was added, which means these 3 blocks were added. These 3 blocks were added, these 3 blocks were added, these 3 blocks were added. Obviously, I'm over counting, so it's these 3 blocks. Don't double count this one. These 2, these 2, these 2, right? So it's 1, 2, 3, 4, 5, 6, 7, 8 blocks that were added, right? And so here, what I did is I noticed a little pattern, right? What I said is like, okay, let's look from n equals 2 to n equals 3. Okay, at n equals 3, so we'll say n equals 3, how many blocks do we need to add, right? So here we'll say the value of n, and here we'll say blocks added, right? And so here we'll say for n is equal to 3, how many blocks do we add, right? Well, we added a total of 1, 2, 3, 4, 5, 6, 7, 8 blocks, right? So we added 8. For n is equal to 4 here, I actually drew it out, and I was like, okay, here's my 3 shape, right? It's this like little beautiful shape over here, which I drew with the T's, the O denoting origin, and so here are the hashtags that I added. And then there's 1, 2, 3, 4. So you'll notice it's 4, 4, 4, and 4. But since obviously we're double counting 3 elements here, we have to always subtract an additional 4, which is literally a number of elements. Essentially, here we'll see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 elements. So for 4, very interesting, we needed to add 12 blocks. Now let's see if there's a little pattern here. For 2, right, how many blocks do we need to add for 2, right? For 2, we went from 1 and we went to 5 blocks. We needed to add 1, 2, 3, 4 blocks, so we added 4. So if you were starting to catch on a little bit, here I was like, okay, what if what's going on is we keep adding by 4 every time, right? And so here I pre-computed the solutions for several cases, and I see that's exactly what happened, right? We have 1 here, then we add 4, which is 5. Then to 5, right, we'll add 4 times 2, and that gives us 13. 13 will add 4 times 3, and that gives us 25. And for 25, we're going to add 4 times 4. And this is exactly how the pattern is going to keep on going, right? Here it's like we added 4 blocks. Here we added 8 blocks. Then we're going to add 12 blocks like we did for case 4. And then if you drew for n equals 5, 6, and so on, you'll see that you'll end up adding 16 blocks, 20 blocks, 24 blocks, which are just kind of confirmed by looking at these numbers over here, right? And so recognizing that pattern, all that's left to do is actually come up with a mathematical formula, right? And so the very first thing I did was like, define this recursively, right? So it's like, okay, here I mapped like, the pattern. So 1 maps to 0. Oh, okay, we can ignore case 1 for now. But the point is that like, for 2, it's like we added 4 blocks. 4 is equal to 1 times 4. For 3, we added 8 blocks. This is equal to 2 times 4. For 4, we added 12 blocks. This is equal to 3 times 4, right? So it's like take the number, subtracted by 1, times 4, that's how many blocks were added. For 3, subtracted by 1, so that's 2 times 4, that's how many blocks were added, right? For 2, subtracted by 1, 1 times 4 is how many blocks were added. And for 1, it's just like, 0 blocks were added, you just start off with 1, right? So it'll be 1 plus something, right? Remember how I said that? And so what I realized is like, okay, it's always the number minus 1, times 4. So that's why I had 4 times the number minus 1 plus the amount of colored cells there was all the way up to n minus 1, right? This is how many colored cells there are for n. It'll be it'll be the number of colored cells at n minus 1 plus this many colored cells that we added, right? Remember, like step 4, we added 3 times 4 number of cells, the 3 being the 4 minus 1 here, or more specifically for 3, we added 2 times 4 amount of cells, right? We added 8, 1, 2, 3, 4, 5, 6, 7, 8 here along the borders, right? With 2 being 3 minus 1 here. And so the point what I'm saying is like, okay, for n, if you want to know the number of colored cells at n, take the number of colored cells at n minus 1, and add to that 4 times n minus 1, right? For example, for 3, it'll be like, the total number of colored cells for n equals 2, and then we're going to add a total of 2 times 4 more cells on top of that. So that's why I'm saying for n, it'll be colored cells of n minus 1 plus however many cells you're adding on top of that, right? So that's why if I have this, I can just return this as long as I have a base case of, if n is equal to 1, then we'll return 1. Otherwise, we'll just keep on doing this, right? Here, might need a self, right? But if I do something like this, it will work just perfectly fine, right? Because it follows this nice little mathematical formula that we had right up here. Now, the only thing is that this is a little slow, understandably so. And so here I was just like, okay, like how can we do even better, right? And what I realized is like, okay, it's just going to be, 1 initially plus 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5, right? So it's essentially a sum where we're going to have 1 plus 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus ... right? Let me copy that on over, right? This is essentially what we're dealing with here. And so here I said, okay, how about it's just 1 plus sum. It'll be, okay, we want 4 times a number. So here I'm going to say C, right? Here we'll even make it a return. 4 times C, 4, C in range. Well, we're going to start with the number 1, right? And we're going to go all the way up to plus, remember, for a specific n, it's up to 3. So it'll be n minus 1 times 4, right? So it'll be up to 4 times n minus 1, right? So here we want to go up to n minus 1 inclusive, so we add 1. So we go up to n, not including n, i.e. all the way up to n minus 1, right? And so if we return this and run this, we'll see that it works as well just fine, right? Now, here's where I did a little bit more funny business, which is like, okay, how about there's a factor of 4 in every single one of them. How about we take them out, right? This is really equal to just, 1 plus 4 times 1 plus 2 plus 3 plus 4 plus ... plus n minus 1, right? So here's like take out the 4 here from the sum, and it'll be 4 times this, right? So here's just doing a little bit of algebra, right? And we can submit this. This works as well, right? And we get actually a little bit of a faster solution. Very nice. And so that's pretty much it. And in fact, we can even shorten this a little bit. C4C in range this is just like, it's just the range 1 comma n itself. So we can even simplify that even further, right? But now, this is just a little mathematical trick that I know. I know that the sum of the first n integers, right, is equal to a particular value. I actually know that the sum of the first n integers, like 1 plus 2 plus 3 plus da 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 up to some index I, right? So here if I do 1 plus 2 plus da 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 plus I, this is actually equal to I times I plus 1 all over 2. This is just a mathematical formula that I know, that I memorized from my discrete mathematics class in my first year at the University of Toronto, Scarborough, which is a nice, very nice little mathematical formula to know. It comes in very, very handy, and I can even prove this by induction, right? So if this is just something you've never seen before, I can essentially do a little bit of a proof, right? Might as well. Here we'll say P of n. If n is greater than or equal to 1, then we'll say, what shall we say? Then 1 plus 2 plus 1 plus n is equal to n times n plus 1 over 2, right? Here we'll say, okay, proof that P of n is true. So it's already vacuously, okay, so it's like if this, then this. So first of all, if this criteria is not met, if n is less than 1, then P of n is already true vacuously. The more interesting case is when n is greater or equal to 1, right? So here we'll do base case, P of 1. Here we have, okay, 1 plus 2 plus da 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 all the way up to n. Well, n is 1, so it'll be 1 itself is equal to, so here we'll say 1 is equal to 1 times 1 plus 1 over 2. So here we'll just say, we'll look at the right hand side, right? This is equal to 1 times 2 over 2 is equal to 1 times 1 equals 1. So true, right? So here, like, the sum of the first n numbers, since n is equal to 1, it'll be just 1 itself. And here, n times 1 plus 1 over 2. 2 over 2 cancels out to a 1. 1 times 1 is just 1. So therefore, this is true as our base case of P of 1, right? Now, want to show I greater or equal to 1. P of I is true. Then P of I plus 1 is also true. Suppose P of I, right? Since P of I, we have that this is true, right? So here we're saying, okay, we've shown that P of 1 is true. We want to show now that if P of I is true for any I greater or equal to 1, then P of I plus 1 is also true. So here I'm saying suppose P of I. Since we have P of I, we have that 1 plus this, so here we'll put an I is equal to this times I plus 1 over 2. Want to show that P of I plus 1 holds, namely that this plus I plus 1 is equal to, this will be I plus 1, this will be I plus 1 over 2. So here we'll take this, we have this, okay, this is equal to, here we'll just wrap this in parentheses just to make it clear, which is equal to, here we'll say it's equal to this plus I plus 1 by induction hypothesis, right? We'll say this is our induction hypothesis, that P of I is true. There we go. Here we'll call this our induction hypothesis. There you go. Meaning we have that here we'll call it IH officially like this. So this is by induction hypothesis. So yeah, so here is like we want to show that this, right, that P of I plus 1 holds, right, that 1 plus da 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 plus I plus 1 is equal to I plus 1 times I plus 1 plus 1 all over 2, right? So here we have, okay, let's look at the left-hand side, which is I1 plus da 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 plus I plus 1. That's what we have. Now I'm just putting a parenthesis around this part because this, we have P of I is true, right? 1 plus da 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 plus I is equal to I times I plus 1 all over 2. So here, that's why I'm substituting that in over here, right? By using my induction hypothesis, here we're supposing that P of I is true, right? We just want to show that if P of I is true, then P of I plus 1 is true. So we're assuming P of I is true. So here, that's why I'm allowed to do my swap because of the induction hypothesis. Here we'll say, well, let's remove everything. So this will be like, you know, I times I, which is really like, you know, I squared plus I. So here's like I times I plus 1 is equal to I squared plus I. And this will be all over 2, right? Plus, and here we'll just put this as a factor of 2. So we'll multiply everything by 2 in here. So this will be 2I plus 2 all over 2, right? And so here, let's combine like terms. So we'll have I squared plus I plus this guy in here, 2I plus 2 all over 2. This is equal to I squared plus 3I plus 2 all over 2. And I will say that this is equal to I plus 1 times I plus 2 over 2. All right, since equals I squared plus, here we'll say plus 2I plus 1I plus 1 times 2 is equal to I squared plus 3I plus 2. There we go. So we are able to factor this out, right? 2 times 1 and 2 plus, so 2 and 1. 2 times 1 makes 2. 2 plus 1 makes 3, right? So we can factor it out this way. And obviously, I plus 1 is simply equal to I plus 2. So we can change this I plus 2 to be the one we have up there. So this will be, you know, I plus 1 from here times I plus 2. But we can rewrite I plus 2 as I plus 1 plus 1. And then again, everything over 2 over 2. Therefore, P of I plus 1 also holds. And therefore, more generally, henceforth, by proof via induction, P of n holds for all n greater or equal to 1. There you go. So there you have it, right? This is a nice little proof, and if anything, I will just leave it in there. But yeah, so like this is a little proof, right? We want to show like, okay, maybe I can, there we go. Maybe things will be a little bit nicer, but here's a proof, right? So my claim is that, okay, the sum of the range of the first n numbers, right? 1 plus 2 plus 3 plus 4 plus all the way up to some n, right? I want to say that, okay, if n is greater or equal to 1, then the sum of the first n numbers is equal to n times n plus 1 all over 2, right? And so here is my little proof. I say P of n, it states that, hey, if n is greater or equal to 1, then this thing is true. I want to show that it's true for all n greater or equal to 1. So the base case will be P of 1, i.e. when n is equal to 1, right? And so here I show, okay, the right-hand side, n times n plus 1 over 2. Well, that's just equal to 1 times 1 plus 1 over 2, which is 1 times 2 over 2. Well, 2 over 2 cancels out to 1, so it'll be 1 times 1, which is equal to 1, which is indeed equal to this, right? 1 plus 2 plus 3 all the way up to n, the sum of the first n numbers. Well, there's only n equals 1 total number, so just the number 1, right? So it's indeed equal to 1, so that's true. All right, now we want to show that for any I greater or equal to 1, if P of I is true, then P of I plus 1 is also true. Let I be arbitrary. So suppose P of I, meaning I greater or equal to 1, be arbitrary. Suppose P of I is true, meaning that we have that 1 plus da 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 plus I is equal to I times I plus 1 over 2, i.e. the same as this predicate over here, which will be our induction hypothesis, right? We want to show that if P of I is true, then P of I plus 1 is true. And here we do exactly that. So we suppose P of I, want to show that P of I plus 1 also holds, so we use our induction hypothesis at some points, right? So we use it right here to essentially do a little bit of math to show that P of I plus 1 also holds, right? And so now we have that, okay, for any I greater or equal to 1, if P of I is true, then P of I plus 1 is true. Now, since P of 1 is true, that means that, which was our base case, since P of 1 is true, by this logic over here, it must mean that P of 1 plus 1 is equal to P of 2 is also true. But since P of 2 is true, then P of 3 must be true. But since P of 3 is true, then P of 4 must be true. And since P of 4 is true, then P of 5 must be true. And P of 6 must be true. And P of 7 must be true. And P of 8 must be true. P of 9 must be true over and over and over and over all the way to infinity. So that's how we say that, okay, this is true for any n greater or equal to 1, right? This is a classical proof by induction where we prove it's true for some base case, and we say that, okay, if it's true for some number I, then it's true for some number for the number I plus 1, right? Which will make it like, go on always over onto infinity, which is pretty nice and sweet. So that way we can essentially, so now that I proved that, right, we can essentially use that result to say, okay, the sum of the first n numbers, well, right, we have 1 plus 2 plus da 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 all the way up to n. Instead of doing an over for loop in here, I can use this nice little mathematical equation now, right, which is exactly what I did. I just have to make sure that I write it in Python notation, right? So here I'll have this and this. All right, now the only problem is that I might not have this as a decimal yet, right? So here, if I come over here, yeah, this is not a valid value, right? So here I just needed to do divide by 2. Yeah, I might need to put a parenthesis here. Oh, and yeah, here it's all the way up to n minus 1, right? So here's like, it's true for some n. That might be a little bit confusing, right? But here's 1 plus 2 plus 3 plus 4, and the last number itself is n minus 1, whatever n is, right? So here's like swap in n minus 1 for this n, right? So this will become like, n minus 1 here. Swap in n minus 1 for this n. Okay, this will become n minus 1 here. And now all of a sudden, this is now true, right? So now this is when we have an extensive solution. Now n minus 1 plus 1 is just n, so we can just refactor this to just be n. Let's not be too silly here, right? And there we go. That is how we have a nice and working solution. And here I can even just get rid of a few of the parentheses, right? But this is why this solution now works, right? Which is 0ms and beats 100%, which is absolutely beautiful. But yeah, this problem just turned out to be, a one-liner mathematical formula. And if anything, I can leave it as is, right? So here, I'll get rid of everything that isn't this guy over here. So here we can just put in this. And there we go. We have a beautiful one-line solution of Python that works absolutely like magic. 0ms beats 100%. But at least now this is not just coming out of nowhere. The full reasoning and rationale behind that logic now, right? So here, if anything, I can paste it. Scratch work as I was solving the problem, right? So I might as well keep all of that in there. Forgive me. There we go. Yeah, I don't know what to keep and what not to keep. Yeah, we can get rid of the solution. That little diagram was nice. But yeah, yeah, we can get rid of a lot of stuff. Maybe I keep my little proof by induction just because it's nice. I just like it. There we go. Right. Solution for first few n. Mappings. Here we'll just make this like this. We'll even make this guy like this. There we go. There we go. And so, yeah, there we go. So now we submit this. This is a nice and working solution. But yeah, so now it's like, this isn't just like black magic. Now you understand the full rationale, right? Which is that we realize that each step we add a certain amount of blocks. The amount of blocks that we add will be n minus 1 times 4 blocks on top of the previous amount of blocks for the previous n, right? So it's like a recursive formula, and then we just worked a lot to essentially figure out how to turn that recursive formula into a mathematical formula, so that obviously we don't have to do much work. It'll just be O of 1, and that's how we get that beautiful 0ms beats 100% solution. And yeah, so hopefully that solution makes sense. And otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.